Alright, so this video is going to start out section 6 for us, and it's just going to be kind of a quick video, basic introduction on triangles. So as it is an introduction, we're going to cover kind of a few things here that kind of have a broad range of topics, but all dealing with triangles and classifications of triangles, and some basic concepts that we need to be familiar with when it comes to triangles. So first of all, when it comes to classifications, this is something that you may already know, but you need to know how to identify triangles by their name, by their type of triangle. And all triangles have two names, one that is based on their angle and one that is based on their sides. So again, one that's the relationship between the angles of the triangle, and then one that's the relationship between the sides of the triangle. So over here on this side, we're going to talk about angles. And then over here, we'll talk about sides. So each of these three triangles on each side have some type of name based on either the relationship of the angles or the relationship of the sides. So first of all, this first triangle, we would call this an acute triangle because all of the angles are acute. If all three angles of a triangle are acute angles, then the triangle is acute. This next one, this is a right angle, so we would call this a right triangle. Now notice, a little unlike the acute triangle, only one of the angles are right angles. Something that you should know that we've talked about before is that every triangle has a sum of 180 degrees. Well, if we had three right angles, that would be 270. So there's simply not enough room for more than one right angle in a right triangle. So if we have just one right angle, we call it a right triangle. And then the last one we have, this angle, it's a little bigger than a right angle. It's an obtuse angle, so we would call this an obtuse triangle. And just like the right triangle, there's just not enough room for more than one within the 180 degrees. So it only has one obtuse angle. Alright, so that's classifying triangles by their angle. Now we also have classifications based on sides. And just like classifying triangles by their angle, there are three different classifications based on the relationships formed by the sides of the right triangles. So the first one, this is the one we have up top here. This is what we would call an equilateral triangle. And what makes an equilateral triangle different than the other two is that all three sides are the same, signified by these hash marks here. Any side that has the same amount of hash marks as another, those sides are congruent to each other. So in this next one, you'll kind of see the difference. In this next triangle, we would show that like this. Notice that this one has two sides that are the same and one that is different. This classification is called an isosceles triangle. So an isosceles triangle. And then the last one, hopefully you figured out by now what this means. All three sides have a different amount of hash marks, meaning all three sides are different. This is what we call a scalene triangle. So there you have it. That's the classifications of triangles based on their angles over here and the relationship between the sides over here. Alright, now we're going to look at two questions. This first one is going to be kind of applying that idea of classifying them, but we're going to look at how do we do that on a coordinate plane. And for these two, we're going to focus on classifying them by their angles. So looking at these two shapes, I'll start with this one. My first inclination would be that this is a right triangle, because I believe that this is a right angle. But we want to be able to prove it using some kind of arithmetic or a theorem or a postulate or arithmetic that goes with a theorem or a postulate or definition of some sort. So for this to be a right angle, that would mean that AC and CB form a right angle. Now this one, it's pretty easy to tell that they definitely do, because AC is a vertical line and CB is a horizontal line, and vertical and horizontal, those lines are perpendicular. So perpendicular, definition of that says that perpendicular meets at a right angle. So this is definitely a right triangle because of that. But what about when it's not perfectly vertical, it's not perfectly perpendicular, where we can't see that it's perfectly perpendicular because it's vertical and horizontal? So something like this. This angle, it kind of looks like a right angle, but I'm not positive that it's a right angle. So the way that we're going to prove that is using the slopes. So I'm going to find the slope of each of these lines. So to find their slopes, and if you don't remember, slope is just rise over run. So from one point to the next, we want to figure out how far it's rising, or if it's going down, so how far it's rising down would be negative. And then the run is the left and right movement. How far is it going over? So we'll start with DE. So we'll find the slope, and slope is represented by M. So we'll find the slope of DE just by looking here and counting this movement. So this goes down 1, 2, 3, 4, 5, and it goes over 1, 2, 3, 4, 5, 6, 7, 8. So the slope of this line is negative 5/8. Now, if this is a right triangle, then the slope of FD will have to be, change colors because this is kind of contingent, it will have to be 8/5. So remember, perpendicular slopes, so right angle, perpendicular slopes are opposite inverses. So flipped, one's positive and one's negative. So let's see if this is that 8/5. If it's not, then we know it's not a right triangle, but then we can use this as well to figure out what would be a right angle, which will help us figure out whether this angle is acute or obtuse, if it is in fact not a right angle. So this one, it goes 1, 2, 3, 4, 5, 6, 7, 8. So it goes up 8. So that's right. So 8. Now let's see if this is 5. 1, 2, 3, 4, 5. So it's not 5, it's actually 7. So the slope of this is actually 8/7, meaning this is not a right triangle. So it's not a right triangle, but we can figure out what type of triangle it would be. So that 0.8, figure out where a right angle would be, so that we have kind of a way to compare this angle to determine if it's bigger or if it's smaller. So I'm just first I'm going to kind of just extend this line out a little further. Let's see if I can do that a little better. Try that one more time. So I'm going to extend that line out a little further, and then 8/7, if it was 8/5, then that point would be right here. So we'll draw a line going through there, and then we can actually see that makes this, so if this line stays the same, and then this one comes out to make it a slope of 8/5 instead of 8/7, then that angle actually gets bigger. So if the angle has to get bigger to be a right angle, then we know that this angle is smaller, and this is an acute triangle. Now, just to add to that, we're not going to go through it in this, we could also figure this out by its sides, whether it's equilateral, scalene, or isosceles, by using the distance formula. So we could use the coordinates and find the distance of FD, the distance of FE, and the distance of DE. But we'll review that in a later video. So finally, we're going to look at just one quick review. Something else that we've talked about with triangles before is that all triangles have an interior sum of 180 degrees. And knowing that, we can calculate the exact measurement of these three angles that we're missing, and then use the measure of those angles to determine what type of triangle this is. Now, just by looking, it kind of looks like an obtuse triangle, but again, this idea that we've had all year, and we don't want to assume anything. We want to be able to prove it. So if the sum of all triangles, of all their interior angles is 180 degrees, what that means for us is that 10x plus 20x plus 30 plus 8x minus 2. I'm actually going to rewrite that so I have a little more room. 20x plus 30 plus 10x plus 8x minus 2. We know that this has to equal that 180 degrees. Now this seems like a long equation at first, but really we have a lot of like terms. So all of our terms with the x, those can be combined. So 20 plus 10 plus 8, that's 38x. And then we can also combine all of the constants together. So we have 30 minus 2, that's 28, equals 180. And then from here, we just have the process of solving this equation. So minus 28, 38x equals 152. And then we divide by 38 to get rid of this 38. So 152 divided by 38 is 4. Now that's not the measure of our angles, but that's the value of x. Now the way that we can apply this is simply plugging the 4 into the x in all three of these expressions, and it will give us the values. But for this, all I'm really going to focus on is plugging it into this one here, because this is the one that I'm not sure about. This is definitely acute. This is definitely acute. But if we find that this is either right or obtuse, we only need one, and we know if this is right or obtuse, that it is a right triangle or an obtuse triangle. If it's acute, then we would need to calculate these two as well just to double check. But if we get 90 or anything larger here, then we don't have to go any further. So 20 times 4 plus 30. Well, 20 times 4 is 80. 80 plus the 30 is 110. And 110 degrees is larger than 90. So since this one angle is 110 degrees, we know that this is an obtuse triangle. So just a quick we can use a coordinate plane using the slopes to determine what type of triangle we have, or we can use expressions and equations using what we know about the sum of all triangles to find the measurement of angles, again, to determine the classification that the triangle is. Is it obtuse? Is it right? Is it acute? We could do this same process here to find the sides to determine if it's equilateral or scalene or isosceles. And on the coordinate plane, we could use the distance formula, which we'll review again in a later video, but we could use the distance formula to determine distances on the coordinate plane to discover whether it's equilateral, isosceles, or scalene.